Ever wonder how your smartphone fits so much power in your pocket? The answer: we've mastered building things unimaginably small. Welcome to Nanotechnology, where we create and control matter at the atomic level, making today's tech possible. Inside your devices are billions of tiny switches, called transistors, smaller than a virus. This isn't science fiction. It's happening right now, thanks to a process that lets us sculpt on surfaces so tiny, we need special microscopes to see them. Without this, our phones would be the size of refrigerators. So, how do we build these microscopic cities inside our gadgets? The answer: nanolithography. Grab your imaginary lab coat. We're about to shrink down and explore the science powering our digital world. Lithography is like high-tech stenciling. Originally, it meant stone writing, but today, it's how we draw patterns on silicon wafers at the nanoscale. Imagine using a stencil and spray paint to make a star, except our paper is silicon and our paint is special materials. Or picture getting a sunburn in a pattern. You use sunscreen and a stencil, and the sun leaves a design on your skin. That's how photolithography works, but with light and chemicals. The patterns we make are so tiny, visible light is too clumsy. So we use extreme ultraviolet, EUV light, with a wavelength thousands of times thinner than a hair. Lithography is simply creating patterns on a surface, defining where to build and where not to. This technique is the foundation of the digital world, turning blank silicon into the brains of computers and smartphones. It's the first crucial step in making modern technology possible. Let's see why making things so small matters so much. Why go so small? It's all about speed, power, and efficiency. Your phone's brain is made of billions of transistors, tiny switches that process information at lightning speed. The smaller and closer together these switches are, the faster signals travel, just like messengers in a compact city. Shrinking transistors means faster devices, more power, and longer battery life. Packing more transistors into chips lets us run complex apps, stunning graphics, and AI. Smaller distances mean less electricity used, good for your battery and the planet. This relentless shrinking is called Moore's Law. Every 2 years, chips double in power and get cheaper. Advances in lithography drive this progress, powering everything from smartphones to life-saving medical tech. Next, let's see how we prepare the perfect canvas for these tiny masterpieces. It all starts with the perfect canvas, a flawless, ultra-clean silicon wafer. These wafers are made in clean rooms far cleaner than hospitals. Even a speck of dust can ruin a chip. The wafer is coated with a light-sensitive material called photoresist, similar to old camera film. A drop of photoresist is spun into an ultra-thin, even layer, thinner than a sheet of paper. The thickness must be controlled with nanometer precision, or the patterns won't work. After coating, the wafer is gently baked to prepare it for the next step. This smooth, perfect layer is essential. Without it, the rest of the process would fail. Now, it's time to draw with light. Here's where the magic happens. Exposure. We use a mask, a super detailed stencil, and shine EUV light through it onto the photoresist-coated wafer. The mask's pattern blocks light in some places and lets it through in others, creating a chemical change in the photoresist. It's like using invisible ink that appears only under a special light. The machine aligns the mask and wafer with nanometer precision, an engineering marvel. This process is repeated across the wafer, imprinting the pattern everywhere. Lithography machines are among the most complex and expensive tools on Earth, operating in a vacuum to protect the delicate process. This is how we transfer intricate circuit designs onto silicon. Next, we reveal and carve these patterns into reality. After exposure, the pattern is invisible, a chemical change in the photoresist. We develop the wafer, washing away exposed areas to reveal a stencil. Now comes etching. Using hot gases or plasma, we carve the pattern into the silicon where it's unprotected. It's like sandblasting a design onto glass, but at the atomic level. The etching must be precise, straight down, no mistakes. After etching, The remaining photoresist is cleaned off, leaving a permanent 3D pattern in the silicon. And this is just one layer. Modern chips have over 100, each perfectly aligned. The process repeats: new layer, new mask, new pattern, building a skyscraper of circuits smaller than your fingernail. This painstaking layer-by-layer construction creates the powerful brains of our digital world. So, what does the future hold for this tiny technology? Lithography lets us build the impossible: faster computers, smarter phones, and more. But the future is even bigger. Nanobots fighting disease, new materials, clean energy, and sensors that protect our environment. Building atom by atom gives us control to solve huge problems. Understanding this science isn't just for experts. It empowers everyone to shape the future. The smaller we go, the bigger the impact. Stay curious, ask questions, and explore the wonders of our universe, from galaxies to transistors. The world of nanotechnology is just beginning. Who knows? The next breakthrough could come from you.